This video is going to illustrate the application of plotting in the FLUX model to show some of the graphs that are useful in navigating your way through the application of the FLUX model. Again, we'll open FLUX version 3.37. And we'll open the save session that we were using before. So again, we're looking at sample dates from 2007 through 2012, and the continuous flow record is 1912 through 2012. Okay, one of the plots that's useful here is to plot flow versus date. And we get this one. I showed this actually in the first video. We have flows from 1912 to 2012. The yellow squares are the sample flow data for the last period of time from 2007 through 2012. We could plot on the vertical axis. We can change the scale to log scale if we wish. And on some plots we'd have time on the horizontal axis or maybe flow, and in that case we could also use a log plot for that as well, but we're not going to do that in this case. Another plot would be flow versus month, because what this will do is to show the distribution of flows during the year. And we can see that here most of the flows are occurring during the spring, let's say late March to late June. That's where most of the flows. There's quite a bit of flow here in the fall, but the majority of flows in the spring, associated with the more heavier rainfall that you have in the spring, but also the snow melt from the spring snow melt. So that plot might help you to understand why we might be getting more sediment during that period of time. If we're looking at some other constituent like nitrate, you might think that you get more nitrate load coming from the spring than the summer or fall, just because there's more flow occurring. The flux estimates are strongly based on the relationship between concentration and concentration and flow. And so it's useful to see that relationship. We did some of that plotting for assignment 1. Let's look at the relationship between concentration and flow for method 1 for our data. The TSS is plotted on the vertical axis, sample flow is plotted on the horizontal axis, and the open diamonds are the sample data. And we can see that the method 1 estimate gives you an inverse relationship between TSS and sample flow. So concentration goes down as flow goes up. If you read about method 1, you'll see that that's basically what method 1 assumes, is that the concentration does go down as flow increases. Now this is all for a single strata. We would get a different result if we were to break the flow up into the strata as we showed before, and I'll illustrate that later. I'll break up the flow into strata and we'll illustrate it for one of the methods. Now let's look at method 2. Again, plot concentration versus flow. And you can see here there's the sample data, and then the estimate with method 2 is the weighted weighted concentration. So this horizontal line just says basically that for all flows within the single strata, the TSS associated with that flow, regardless of the flow, because it's for the entire range of flow, the concentration will be the value that's given here of about 17,000 microgram per liter of TSS. And then let's look at method 6. Now, method 6 fits a regression line to the data. We can see that it's not a constant as shown before. This is the relationship between TSS and flow for the method 6 application. You can see that there's still quite a bit of scatter around the data points. We can look at the statistics for that fit, and they're given here. So you get an idea as to what how good the fit is of the that equation, that regression equation for method 6 to the relationship between TSS and flow. We'll come back later and we'll look at the we'll take a look at the stratification of the flow data. One of the things that we did in the first assignment was to look at the flow duration curve, or flow exceedance duration curve, and that was a time-based. We can use volume-based here as well, but time-based is what we used. So let's plot that. And here, remember that in assignment 1 we used a log scale on the vertical axis, so we'll plot that on a log scale. And we get that, and then on the horizontal axis for the percentages of exceedance we had a linear scale, so we'll go back and change the bottom axis to a linear scale. So this should look very similar to what we had, or what you found in assignment 1, the relationship between discharge, except for we were using cubic feet per second. Here is million cubic feet per year. It's just a units conversion. The upside down triangles are the grab sample values of TSS associated with so you shouldn't expect that those values are going to plot around the flow duration curve, because the green line that you see here is not the load duration curve, it is the flow duration curve. The what look like open circles are the actual flow duration based on the sample flow data. I'm not aware of exactly how the FLUX model calculates the position that each of those values takes, that is, the exceedance value associated with them. But it's nice to see the fact that the two curves, they are different, but the fact that they're somewhat similar might tell you that there's some good representation of flows within the sample record. We can do sample flow versus total flow, and okay, so if we come down here, look at let's see, that's not exactly the graph I was looking for. Okay, histogram comparing flows, daily flows with sample flows. So just to show the representativeness of the sample flows, this illustrates the basically the ranges of flows given here, and how the sample flows and the daily flows are represented in the record. So you might say that there are some differences between the sample flows and the daily flows. So one might say that, well, maybe we need to take here more sample flows, let's say in the low range, so that we get a better representation of the low flows, more representation of the flows in this range, and also here. In the higher flows, it appears to be that there's more a better comparison between the sample flows and the daily flows. One other plot that's very useful is to plot the residuals of the relationship, for instance, between concentration and flow. So if you try to predict the flow with a given model, or predict the concentration as a function of flow with a given model, you'll have some residuals or differences between the predicted and the observed value. So here we'll plot the concentration estimate, and this is for method number 6. This is the residual, this is the TSS, and so we can see that here there appears to be no bias. The residuals are positive and negative, approximately the same amount on either side, from 0.7 to minus 0.75. Now if you read the FLUX manual, you'll find out that the residuals are calculated by taking the ratio of the observed to the predicted value, and the logarithm of that ratio is taken. So that's why the numbers are the way that they are. The residual is not calculated by taking the difference between the predicted and the observed, but by taking the ratio of them and then just basically taking the logarithm of that. And what we'd like to see for the residual of a particular method is that there's no bias as a function of concentration. We would like to see that there's no bias as a function of date or of flow magnitude, and so we can do those different plots here. That was the one for residual versus concentration. We can look at it residual value versus flow. Again, this is for method number 6, and it appears the range here is 0.75 to minus 0.75, and again, doesn't really appear to be any bias in the result. We could also look at it versus date or month, so maybe the residual is somewhat a function of time of year. And again, it appears that the residuals are not dependent on that, the monthly period either. Let's go back and we'll try method 2. And we'll plot the residuals for that one versus concentration. We'll do it versus month, for instance, and we can see that there is some bias in this case for method 2. Much larger negative residuals at a given month than what you see for the positive residuals. It's unbalanced. And then if we do it versus flow, there again we do see that there appears to be some bias, that at the lower flows there's a much larger negative residual than positive residual, so it does appear to be unbalanced down there as well. Now we can improve some of the methods. For instance, method 2, make it so we can reduce some of those residuals by stratifying the data. So let's go in and we'll stratify. We'll make the 4 strata as we had before. And let's plot the residuals in this case. So in the first regime, flow regime, we've got this range, which is not too far off. It's somewhat balanced here. Appears to be fairly balanced here, and then also back here at the highest flow stratum. So the residuals appear to be fairly balanced. We didn't find that for method 2 when we had the single stratum, when all the data were pooled together. There was more of a bias on the negative residuals. You can also look at this for flow. We see that the range, before we had much larger imbalance, or we had an imbalance in the residuals. For method 2 here, they are fairly good, almost like what method 6 was when we just had the pooled data. And we can also test it versus month. Again, they appear to be fairly balanced within the over the entire period of time. So the residuals are useful in helping us, or should be viewed as being useful, helping us to understand which model is the best one to fit. We found that when we increased the number of strata, our estimates of load became more uniform among the different methods, indicating probably that the estimates are better. Coefficient of variations generally decreased, which would indicate that the mean estimates are better estimates, because there's less uncertainty in that estimate. And we also saw that probably the reason why we got improvements was because the model that fits the concentration to flow relationship, that is TSS to flow relationship, got better, had fewer smaller residuals and less bias in the fit as the number of flow strata increased. So I would recommend that you use the residuals in doing some of your analysis, just to prove to yourself that the results are improving based on that better relationship between concentration and flow. Now, currently I have this set up with the data file set up with 4 strata. Let's look back again now at the relationship between concentration and flow. We'll see what the that relationship looks like. And here we've got the 4 strata, and those do show, this is for method number 2. Each of these are the flow weighted mean concentration, flow weighted mean over the sample range, or over the flow range associated with a particular strata. And if we look at method 6, we have that relationship.